Hello and welcome to Nodes 2020. I am Reshma Sheikh of the community group Data Umbrella. We are an inclusive community for underrepresented persons in data science, machine learning, and artificial intelligence. We are on all social media platforms with Data Umbrella. We have a fabulous library of videos on YouTube on data science topics, so please check it out. Thank you. Next, I'm going to introduce our speakers. The title of their talk is RDBMS and SQL to Neo4j and Cypher, Transitioning to the Right Technology for Your Data. Our presenters are Jonathan Gentsch and Robert Vrooman. John is a technology industry veteran with over 13 years experience in complex software development. As a CrossCode senior software engineer, John's dynamic engineering expertise translates the technical aspects of designing extensible data models into scalable solutions, including transitioning real-world data, modeling the schema, and optimizing mechanisms around backend storage. Robert has 7 years experience as a full-stack engineer with a specialization in Spring Boot development. As a software engineer at CrossCode, Rob is responsible for creating pluggable architecture around the decomposition agents that retrieve external data. Rob's expert focus on building processes, continuous integration and deployment, and rigorous CI/CD practices drives innovation across the whole team. Welcome, Jonathan and Robert.
Thank you for that introduction. Hello, this is RDBMS and SQL to Neo4j and Cypher. Today we will be discussing transitioning to the right technology for your data. But first, let's get into introductions. Rob, how about you introduce yourself?
Hi, everyone. I'm Rob Vrooman. I am a senior software engineer at CrossCode. I have 7 years of experience specializing in API development in Spring Boot. Before working at CrossCode, John and I were colleagues at a company called Cofense, where we specialized in malware detection and fraud ring analysis. This is what really led me to becoming a graph evangelist, I would say. And when CrossCode approached us both with a business opportunity of decomposing software artifacts to map out their dependencies, I realized this was a great use case for graph, and that leads us to this talk.
Thank you, Rob. My name is John. I'm also a senior software engineer at CrossCode. And as Rob mentioned, we've worked together in our previous job. And prior to that, I worked in manufacturing environments and even school safety software. But in manufacturing, I did ERP applications and production management software that led me to extensive experience in MS SQL, Postgres, and even MySQL for relational databases. Graph is somewhat new to me as well, and we've been really having a great time using it in our new software. So let's go ahead and check out the agenda for this. To start off, we'll look at relational databases, their strengths and weaknesses. We'll also look at indicators of graph-like data so that you can tell if you have graph data that you might need to switch over. And then we'll take a peek at CrossCode's old schema in Postgres. After that, we will take a look at graph databases, their strengths and weaknesses. We'll look at switching data sources in Java and Spring related to the entity definitions and things like that. And then we'll look at CrossCode's new schema in Neo4j to see how the transition worked out for us. And then finally, Rob will do a demo of CrossCode's decomposition software to demonstrate the data that we can accomplish in Neo4j. Starting off with relational databases and their strengths and weaknesses. Relational databases are actually really awesome systems. They're great for their appropriate use cases. And major RDBM systems are very mature. They're ACID compliant and then been around for decades. So it's not hard to find, it's not as difficult to find individuals who are skilled in SQL querying and doing data design there, because that set of knowledge has been out there for so long. We also see the strengths in terms of data for relational databases. The RDBMSs are really great at time-oriented data, financial data, things with production, anything you would like to roll up. They're great at data aggregation, pivots and cubes, and those sorts of things. A lot of data mining can be done there. But this discussion is in the context of graph data. So in the weaknesses of relational databases, there's some issues that come up when you're dealing with RDBMS and graph data. The big one is that while you are storing the data in tables and it might be normalized and it might be great, the graph is still calculated at query time. And then you have to do some additional processing on the back end to match out extra information or to do more analysis that way. And as you grow in your entity types in your graphs data model, you end up with extra relationships. They require index usage. They require extra joins. All those can cause some development slowdowns and performance issues, and become difficult to manage as well. And then the ORM can be difficult to maintain, but that depends on the implementation. If you have a highly normalized data set, maybe you're using inherited tables and you have a well-defined object-oriented data model for your entities in your code, then the ORM can be fine. And so that just depends on the situation you're in. In our case, it wasn't that great. So when we talk about RDBMS graph schemas that you'll see in the wild, we need to identify if you're looking at your data set, if you're coming onto a new project, you've been handed a project, or you're looking at example data online. There are three major styles that you'll see of graph data implemented in relational databases. One is sparse tables. The second is satellite tables. And third, we'll look at JSON data, which is a variant and kind of a compromise between those two. Up first, we have sparse tables. And this is an example of a sparse table at the top of this slide. What we can see here, let's take a look. We have definitions that are common across all entities. We have asset identifiers, names, types, and subtypes. But then we have additional fields that only relate to the particular type of entity that that record is handling. The first issue here is this is not normalized data. So if you're dealing with a data model in general, you should have your data normalized in your schema. All columns end up existing into the same table. So what this ends up happening is as you scale out the entity types that you're trying to deal with, you'll have to add more columns. You'll have more null fields. And if you want to index any of these you're having to deal with null fields that are being indexed, where you have to account for the null fields. If you want, you can't do default values for these columns at all, because then they'll fill out the columns where you don't want to default for maybe say the OS name when you're dealing with a column username. It has nothing to do with it, so you can't do any defaults. But on the positive side, it is simple to implement. So what you'll see is that this is probably most common in starter projects. And if you're prototyping graph-like data in your RDBMS, it often starts off like this. So this is just kind of the first step, and then what will happen is generally as it grows, you'll normalize the data and into satellite tables, which we'll look at next. On the right, we just have a simple table definition, just so it's a little more clear what we're looking at in terms of data types and all the field names and things like that, in case it's hard to see. The other issue is that table migrations or schema migrations can cause locking issues in this. So if we're going to add a column, this is going to create a situation where it has to affect all records. It's not just affecting a table or deleting a column for that matter. It's not just affecting a table that's just only handling machines or columns. And so as that scales, it has performance issues. So we'll move on to what I think is the most common scenario, and that is satellite tables. Now, I don't have a visual example because essentially it's the same. It's just normalized data. We see the table definitions on the right-hand side. So what are the scenario where you end up with satellite tables? Well, normalizing sparse tables will result in a satellite table situation. The entity types are, each entity type has its own table. So we have a columns table, and machines, and source files. Now the advantage to this is that you end up with the ability to say, set default values. You can index a field knowing it's all relevant to the data in that table. Yeah, and so the other advantage is that the data access is distributed across all these tables. So, you know, if you're trying to insert a bunch of records into, let's say, the machines table, you're not affecting the performance of the columns or the source files table. If you're running migrations against, say, the machines table, let's say you need to replace, maybe there was a bug and you had to just replace all the OS names that got put in there, that update will only occur then to that table. Adding columns, deleting columns, setting default values, only those tables. So it's a much more performance situation. That's the standard normalization benefits that you get in RDBMSs. On the other hand, the problem with this is that the joins can increase with all these tables. As you add more entity types, you have to add more tables. And so you end up with a situation where you're trying to traverse your tree, join out to those tables as well, depending on the type of entity you're looking at, and then maybe filter or do some analysis. It becomes very cumbersome in an RDBMS to do that. And we'll look at a query later on that will illustrate that. But up next, we have JSON data fields, which is the compromise between the two of those. So it's kind of like a sparse table in that it's all in the same table, but it doesn't have the same schema issues that you end up with in sparse tables. You're just doing a JSON column instead. So it's kind of like a schemaless situation or a NoSQL kind of hybrid. And what's nice about the JSON data type is that it's native to MySQL and Postgres. It has better scalability because you're not dealing with the joins out to the various tables in order to get the content data about that entity. So if we look at the username, that middle column or that middle row, you can see that it's a column type. It has a data type, varchar 100, etc. And none of those are shared with the other schemas or the other JSON format for each other entity type. That illustrates also a con in this. The drawback is that the JSON schema is not enforced by the RDBMS in this case. It needs to be enforced in the backend by your code, and that just requires you to do that. There's still no native graph traversal in this scenario. You're still having to do the recursive queries. You're still trying to build up your trees. Everything's still calculated at query time. And querying still has its challenges as a result. So let's take a look at the prior RDBMS schema for CrossCode to see what we have. When we started here, we were assessing the data model of the existing code base. And what we're looking at here is actually a screen grab from Neo4j browser. And the data here is populated by our new software, our decomposition software, that analyzed our old software and was able to present this to us as a graph data set that actually helps us analyze this. So the pink circles represent tables, and the red circles represent columns. And if we look at this one in the middle, this pink table in the middle, it's an assets table. It contains a column of an ID field, which is what you would expect. But what we notice in this is that there are a ton of foreign key references. And so that tells me that this is most likely a satellite table situation. We have a couple tables that look like they're creating the relationships. This is inbound, outbound relationship to the assets table. And there are some other tables that are dealing with that data and relating it out as well. As we scale out the entity types here in the various models that we're trying to capture, this becomes very cumbersome to look at. And then also there's some issues with the column naming for the foreign key references is inconsistent. You can see there's an SID with no space or underscore. This one has an underscore. This one doesn't have an ID. It presented kind of made us nervous looking at it. So we'll go ahead and take a look at the code in the back end to kind of complete the picture here. So on the left-hand side, we see an entity definition for the assets table for an assets class. It has your standard table definition at the top and the schema with CCDB. And we have fields for ID, name, asset identifier, and the type. And this is just the standard stuff that you would see. There's nothing that really concerns me in here. But if you had sparse tables, you would see additional fields that aren't relevant for your particular type. There is code that's not being used for every usage or every purpose of that class. It's kind of some duplication and waste there. What does concern us is when we look at the relationships on the right-hand side, we see a mixture of lazy and eager loading fetch types. And then we see some interesting items at the bottom, say like this DB connections. So a machine or an application might have a DB connection, probably I would say application in this case. But a column definition wouldn't have a DB connection to it, or it doesn't connect out to anything. So here we have a relationship to a data set that's not always going to be used for most of the assets that are in this base piece. Another issue that we see is this eager loading, one-to-many, matched by dependent assets, which this is our relationship table. I didn't place it into the prior slides because screen real estate was important. We just go with the idea that it's a parent and child type ID relationship situation. So if we load this asset and it has dependent assets, this eager loading is going to go ahead and load up these dependency assets. And then as a result, if they have dependent assets, it ends up loading up the whole tree. So in our code, we already are running into a situation where we can't control the tree loading or the cascading event in the same way that we can in, say, a graph situation. So at this point, I'm going to hand this off to Rob, who is going to talk about graph databases.
Thank you, John. So what are the strengths and weaknesses of graph-based databases? So the rest of this talk comes from a lens, not of graph-based databases experts, but of developers who were previously using RDBMS systems and did research and prototypes to determine what was the best solution for our current needs. And we're hoping to share what we came across with you, the audience, and hopefully it is useful to you. So one of the strengths that we determined graph-based databases have is the fact that it is schemaless. And by this, we mean you do not require a migration script to add more data to any particular node. In fact, if the data is additive only, you can do so straight through the code or the OGM, the object graph mapper. And the next time you insert data, that data will be available with no migration script needed. Another strength is that these relationships, instead of being joins, are first-class entities themselves. And this means that the graph is traversed by walking these relationships instead of by joining. This gives us two positives, one of which is the relationships themselves can have additional metadata associated with them. For example, in CrossCode software, we add additional property called confidence level. Basically, if our software is able to decompose that a certain jar contains a given class file, we are 100% certain that the jar contains a class file. However, if this method is calling out to a queue, and that queue message is later read off in a separate software system, there comes a point where an indirect relationship isn't so confident. And being able to set metadata about relationships is very helpful. If there's one thing, a key takeaway from this presentation, I'd like it to be that if your data is focused on the relationships rather than the properties, graph databases may be the right solution for you. What is another reason at CrossCode we chose to go with graph databases and Neo4j? One of which is graph-based analytics. And Neo4j specifically provides a graph data sciences library with many algorithms implemented for you right out of the box. We have yet to implement these at CrossCode, but we've done some preliminary research and found that the centrality algorithm for graphs would be very useful in determining if a particular software artifact is highly coupled. If many things are calling through a particular artifact, the centrality coefficient would increase, and it allows us to do reporting on whether or not there's high coupling or low cohesion in your software system. And finally, if you're worried about transitioning from SQL, if you have a lot of experience in SQL and wonder if the Cypher language is easy to understand, the language itself has practically the same mental model as SQL and is very intuitive. And Cypher is quickly becoming the industry standard for a graph-based query language, and has been adopted by major industry leaders. So what are the weaknesses we came across when transitioning from Postgres to Neo4j? Well, in our particular use case, we found that blobs in a large number of properties should not be stored on a given node. The reason for this being that if a particular node has a blob or a large number of properties, the time to traverse the graph increases, and you can see a large performance hit as a result. However, there's a common workaround to store blobs that we, in fact, do use at CrossCode. Say, for example, you'd like to store a software artifact related to a given node. You simply create an ID for that artifact and store the ID as a property on the node. And that ID could be anything from an ID in another database to a link to an S3 bucket. But doing this allows you to store larger objects related to a given node. Another weakness calls back to the fact that graph-based databases should be relationship-centric. If you find that your data is write often and read little, perhaps in an event sourcing system or a transactional log for financial data, graph-based database strengths come from the analysis between relationships, and you may find that RDBMS or a different database or data source is right for you. A red flag when you're first starting to prototype with a graph-based database that we've seen is that if you find many of your queries are looking up nodes directly based on their properties and not through relationships, a graph database may not be right for you. And finally, though time series data is supported in graph-based databases through the construction of a time tree, where you perhaps put the year and then branch that year off into months all the way down to seconds, etc., and then link those nodes through relationships out to your given data, this solution can become cumbersome, and it might not be the correct solution for you. So this slide is mostly an indicator of how easy it was to transition from our Postgres ORM to Neo4j, Spring Data, and its OGM, Object Graph Mapper or Object Relational Mapper. Without taking a close look at this, the two practically look identical. But if we take a look at the top left base node, you see the difference between the previous CrossCode information is that this is labeled as a node entity. And the relationships, instead of being a join of one-to-one or many-to-many, are labeled as at relationships. And these relationships themselves are entities as described in the top right. And those entities can contain, as mentioned before, a confidence level or interval. So here's a screenshot taking of our version 2, a piece of our version 2 schema in CrossCode. Basically, this is indicating that the dependency tree is actually mapped out in the database itself, how you would draw it on a whiteboard. A package entity, for example, a jar, a war, or an ear file when talking about Java, can contain many source files, and these source files may contain class definitions or interface entities. And this all goes all the way down through method entities and field entities that may call out to a queue, they may call out to a given column. And this information soon in CrossCode's roadmap will include cloud infrastructure and deployment related information. This screenshot here indicates us the ability to take a specific starting point and query for an impact analysis, which we will see in an upcoming slide. Basically, if I was to query for a given method entity starting point, I can take all the relationships coming off of that node to determine if I made a change on this method, what am I impacting? Here we see an example query that is actually used in version 2 of CrossCode software at the moment. This query is meant to find a given subgraph for comparison, and I'll go into more detail on what this is actually doing. So the Cypher query itself is meant to match all of the paths from a starting node to a given depth, and then to its other end of the relationship. We're passing in a given node identity and collecting all of these paths. Finally, we're using the APOC procedures plugin that Neo4j provides to convert these paths to a tree. The result of this is that we can query for a tree with a given starting point. For example, if you have a database deployed in 2 different regions, our software can decompose the database and make sure all of the schemas are the same, and that there is no difference between multiple trees. This is difficult to accomplish in SQL, as you can see, mostly because with any starting node and any given depth, it is difficult to determine what tables to join together. This can be any asset, it could be any subtype. And with the satellite tables, as John had mentioned before, joining these all together recursively becomes very cumbersome and impacts performance negatively. I do have an asterisk on this Cypher query though, because as of right now, parameter maps cannot be used in match statements. They can only be used in the where statements and collect statements. And therefore, to make this work in CrossCode software, basically we had to do the validation of this parameter ourselves, make sure there's no injection attack going on there, and manually replace the query string to get it to execute. So of all the graph databases, why did we choose Neo4j specifically? One of which is CrossCode is a startup company, and Neo4j has offered us an excellent startup program, as it offers many companies. The startup program will allow you to use business level enterprise features if you have below a certain number of employees and below a certain amount of revenue. If you'd like to find out what that is, I would suggest going to their website. But also, we chose Neo4j specifically because of the maturity. As seen before in the previous slide, we are already using a plugin for Neo4j, the APOC procedures plugin. And because Neo4j has been around for a while, the community and the number of out-of-the-box solutions is, from my experience, the most of the graph-based databases. And the final bullet point is less important, as more graph-based databases are becoming so. But if you'd like to do ACID-compliant transactions, Neo4j does support that. So without further ado, I will bring up an example of CrossCode's decomposition data so we can take a look at what's actually going on. So here I am sharing the Neo4j browser with a database I have previously seeded using CrossCode version 2 software against itself and a ServiceNow instance. So to just take a quick look at this, I will select the Java executable we have prepared. So this Java executable has an identity of CrossCode Core Services. This was our previous version 1 CrossCode Core Services jar, and this jar can contain many source files. One question that was brought to me by management before is, if we had a CVE relationship or a common vulnerability and exposure, how could we determine the impact of that vulnerability and our exposure to said vulnerability? As we are decomposing the software, we can take a look at a given class. For example, CVE data, expand this one out. And this source file contains a class definition. The CV data is our DTO object for our CVE class. So I'll just expand this one out as well. Now this class definition, we can see, contains multiple fields and method definitions. But what's more interesting here is that from our decomposition, we've determined that the CVE class is referencing the vulnerability CVE table. I'm going to take a look at this table. This table contains many column definitions, and you can see that the CVE class has many method definitions that reference columns in this particular table. Well, this is well and good for a business analyst who may want to manually click through your decomposition to determine impacts. One question is, how would we do this same walkthrough that I've presented here in a Cypher query? I have a query pre-prepared for that, and I will walk through this shortly. Here is a simple Cypher query that basically retrieves the same information. I'm currently saying match all of the paths starting with a given column out to a depth of 5. Now this column should have a name of vulnerability CVE ID and return all of the paths from this query. So the result, very quickly, as you can see, it's traversed all of the relationships. It's given me the same information. The vulnerability CVE column has a reference link all the way back to the CrossCode core services jar that we've walked through earlier. Not only this, that the vulnerability CVE column has a reference link all the way back to its originating database. And this type of information, being able to query relationships like this, is great for impact analysis if you want to determine what impact a change to a method will have. CrossCode is able to support this through the use of Neo4j in graph-based databases. One other query I'd like to demonstrate is the one on the previous slide, which brought up the APOC procedures plugin. So this is a relatively simple query when you take a look at it, but what it's doing here is taking all of the nodes out to a depth of 2 from the given jar, as we've seen before, collecting them and converting them to a JSON tree. Being able to convert all of the paths to a JSON tree allows you to do comparisons to a JSON structure format. It also allows you to send this information via an API if required. And the APOC procedures plugin was very useful for our use case. I have one last query that I'll go into more detail about, but as of version 2 of CrossCode, our software now decomposes ServiceNow instances. And this is just a basic query to find incident scripts in a ServiceNow instance. And I will let John talk to more about what this query is actually representing.
Thank you, Rob. So what we're looking at is just a tiny portion of the data set regarding a ServiceNow instance. So with ServiceNow, a lot of what is dealt with there is modifying JavaScripts. It's an abstract kind of infrastructure that allows people to customize the behavior of the default ServiceNow applications and plugins and things like that. So there are different, I think they're like service management, or the people who manage the customers' instances. And these companies will have multiple clients that they're trying to manage all their different modifications and just manage instances. So what they'll do is they'll make a modification for one customer and do some JavaScript changes. They might add some fields or change something there. And then they might do a different kind of change to another customer and their code that is running on ServiceNow. And then they might have a change that applies to all of them. And so one of the common applications in ServiceNow is the incident tracking system. And this is just a small example just to kind of illustrate the point. The problem that they have is if they're going to change a JavaScript file, or they're going to change a column, which the green circle is a column representing parent, you can tell that this is going to impact this link script, and then the incident script is also impacted by any changes by the incident table. And so what this will allow them to do is do impact analysis on modifications. And especially with that APOC tree traversal, I think we'll be able to do comparisons between baseline code versus their modifications, so they can figure out where they're modifying things. This is just a powerful start. So thank you, Rob.
It should be noted that of the ServiceNow instance itself, that is really a small amount of nodes, just to illustrate a point. The ServiceNow instance we decomposed roughly comprises 115,000 of the given nodes in this example database, and probably the similar amount of relationship types, with little to no performance impact of the traversals you've seen in these queries. So I will give it back to John to fill out the rest of the presentation.
All right, thank you, Rob. So that concludes our demo of our software. We have a page of references. We highly encourage you to take a look at these. Rob, did you have any comments about, I think, especially the second one, but can you talk about these references?
Yeah, sure. The second one in particular more applies to CrossCode's use case than graph-based databases itself. But this was a white paper written for a conference detailing the benefits and drawbacks of using a graph-based database for software artifact decomposition, which is exactly what we're doing. So we're able to find a community quite quickly using a graph-based system for similar business use cases. And another thing I'd like the audience to take from this presentation is always try to look into the community to see if someone is doing something similar.
Cool, thank you. So we'll go ahead and take a look at where we're going in 2021. This is our roadmap. So we already discussed having Java decomposition and ServiceNow decomposition. As well, we already support all major relational databases through JDB connections. Anything that supports a JDBC connection, we can decompose. Moving along, we will be expanding our platform decomposition to Device42 and AWS. Very excited about the AWS one. That will be a lot of fun. We'll be able to tell how your infrastructure is connecting to your with your software and how they all relate. Machines communicating to machines, this sort of thing. And then we'll be expanding the languages, the Node.js, React, other compiled languages, and eventually Python, scripting languages like Ruby. And then message queues, we currently support MSMQ at a basic level at the moment, but that's expanding, and we're working on that right now. We were going to expand into Hazelcast, RabbitMQ, and Kafka. And then data storage, we're excited to get into MongoDB, decomposition, and any of the other ones like Cassandra, Redis, and object storage like S3. Eventually, we'll get into infrastructure work as well. And so this concludes our presentation, and we'll be open to questions, of course.